Welcome to our demonstration of Train, a cutting-edge causal intelligence platform transforming enterprise decision-making. Train leverages the power of cumulative internal and external expertise in business, operations, and engineering to optimize multidisciplinary functions. Today, we will demonstrate how the Train platform revolutionizes the way enterprises approach complex problems, from intricate data analysis to strategic decision-making. Let's set some context for the demonstration you're about to see. Energy companies transport crude oil through hundreds of miles of pipeline network. They strategically place pumping stations in the pipeline network to sustain pressure and ensure a continuous oil flow. These pipelines traverse through potentially hostile areas, susceptible to sabotage, and are also exposed to extreme weather conditions. As a result, energy companies often encounter pipeline leakages caused by natural and human factors. Any such leakage, if not remediated promptly, results in significant operational losses and creates serious safety and environmental issues. Therefore, it is crucial to promptly detect pipeline leaks and remediate those to maintain operational reliability. Train introduces an automated pipeline leak detection application agent based on causal theory. It seamlessly integrates into existing asset performance monitoring processes and scales across large pipeline networks. Today, we will see how Train's leak detection agent complements asset performance monitoring systems used in pipeline maintenance. The agent aims for rapid analysis and minimization of false alarms. Its primary objective is early detection, emphasizing the operator's speed in identifying pipeline leaks and key process variables affected by the leakage. Using cumulative knowledge of petroleum products, physics, the chemistry of liquid transportation, pipeline systems, pumping, and transportation operation processes, Train's leak detection agent autonomously formulates hypotheses, identifies flow anomalies, and localizes leak location in minutes. In the following demonstration, let's consider that I am the lead operations reliability manager for a lengthy pipeline system. I'm responsible for detecting leakage in the pipeline efficiently and for the formulation and distribution of the remedial actions. Here, we look at a long pipeline network with 4 pumping stations joining 3 pipeline segments. The pipeline is installed with various sensors in the pumping stations. A SCADA system aggregates all the data from the sensors, controllers, and equipment. We can access this data from the central server. Now, I have been tasked to analyze this data and quickly detect any ongoing leak with minimal false alarms. We wrestle with 3 operational challenges in a conventional data-centric leak detection approach. First, we understand that ambiguous indicators can complicate analysis and lead to errors. Here, we formulate hypotheses for potential leaks based on pressure drop, as leaks often result in decreased pressure or flow. It's crucial to recognize that process or flow losses may occur in non-leak scenarios involving temperature, density, or petroleum product quality variations. Second, when we analyze a specific pipeline segment within a larger network, we often find the data for the specific segment entwined with the dynamic interactions among the other segments. This interconnectivity makes leak detection and isolation more challenging. Third, the smaller size of the leakage sometimes makes detection very hard. For instance, pinpoint damage in the form of small fluid leakage is difficult to identify, as the pump may occasionally offset the pressure loss. Now let's see how the Train leak detection agent helps us with minimal false alarms in leak localization despite the above challenges. Let's get a bit familiar with the platform. First, we load the historical time series SCADA data encompassing diverse sensor readings at the pumping stations. Data is captured at 1 reading per minute, including pressure, flow, pump speed, specific gravity, temperature, and volume balance. We have loaded together 15 months of data, 3 months each for the first 2 segments and 9 months for the last segment. Now we need to analyze this historical data chronologically, identifying the time and location of any potential leakage. Before beginning this analysis, we've ingested knowledge of liquid transportation, pumping and piping systems, operation processes, and asset performance tracking details into Train. Train represented the cumulative knowledge of the systems and processes as a causal model depicting the leak detection process. Leak detection agent workflow interacts with the causal models and guides me to systemically discover the flow anomalies and localize a leak location in time. First, we are creating a project to formally start the analysis process. The project setup contains multiple analysis sessions. We can create and define individual sessions targeted to the analysis context at any point. For example, we have created sessions for normal and transient scenario analyses. After we created the project, we loaded a list of hypotheses into it. We can formulate these hypotheses manually or leverage Train's machine teaching process to generate them automatically. After loading the hypotheses in the project, we review them and either accept or reject each of them, depending on the final analysis in mind. Each accepted hypothesis becomes available to be part of the analysis sessions created in the next step. In this step, we create analysis sessions. Here we created 2 sessions, one for the normal and one for the transient scenario. I can see the approved hypotheses from the previous step and assign them to appropriate sessions based on the hypothesis context. At this stage, the agent automatically guides us in deducing each hypothesis into important parameters, such as subject, context, relationship, null hypotheses, assumptions, and dependent and independent variables. These parameters are critical for the subsequent analysis. In causal theory, the independent variables are the causes, and the dependent variables represent the effects. Simultaneously, we loaded 2 datasets, one each for creating the causal session signature. In the data field mapping step, we mapped individual data columns to the respective domain concepts. These domain concepts are part of the domain ontology created by Train's machine teaching process. To optimize the labor-intensive mapping process, the agent recommends the closest matched domain concept for each column based on available information. After mapping the data columns, we returned to the hypothesis session page and proceeded with the causal intervention workflow. Like data column mapping, we now associate the independent and dependent variables with the domain concept. This completes mapping the hypothesis parameters to the domain concept and the data column, preparing the agent for causal analysis. Then we generate a causal graph using data for each session. This graph depicts the structural causal model and captures the Bayesian relations across the domain concepts with their mapping to the data column. However, this relation is restricted to only the data in hand, but it also is important to understand what else can influence the effects or the dependent variables we are considering in this scope. That's where data agnostic principles and rational causal models automatically generated by Train augment additional causes as treatment. At this point, the agent prompts us to bring data representing the new treatment so that these new treatments can be instrumental in the intervention. The agent gives us the additional SME causal knowledge insertion as an explicit cause-effect pair in the next step. Subsequently, the agent aggregates the structural, principal, and rational causal models and the SME cause-effect pairs into a single combined causal model representation. Finally, the model generates a causal signature for each session using the combined causal model and normal transient data with no leak scenario. Acknowledging that a sole cause doesn't independently influence an outcome, we must appropriately condition other causes. The leakage agent independently explores various front door, back door, and instrument variable analyses. It challenges the derived causal effect under different stress scenarios, and ultimately establishing the final validated hypotheses and a session-based causal signature. In the final step, aided by the Train leakage detection agent, we scrutinize historical or real-time data by selecting relevant information from the loaded datasets already mapped with causal models. We select the appropriate analysis data from the already loaded datasets. The leakage analysis agent presents the data in moving windows, assigning a risk score to each time window. The time window shifts after each analysis iteration, with a new position partially overlapping with the previous one. We can configure the time window and sliding length. The agent automatically marks each time window into a shutdown window, a normal window with a lower leak likelihood, and a normal window with a higher leak likelihood. We can further identify the probable leak by selecting specific patterns like consecutive higher leak windows followed by long shutdown. As we see here, using this pattern, We discovered a probable leak on the third pipeline segment on August 30th at 1:31 a.m. The agent identifies the likelihood of a leak by assessing the alignment between each hypothesis's cause and effect and its corresponding causal signature. Each misalignment contributes to the anomaly score. The higher the anomaly score, the higher the leak likelihood. In summary, using the Train leak detection application agent, my leakage investigation, once limited to retrospective analysis, has now become near real-time. Now I can simultaneously analyze multiple pipeline segments without additional instrumentation. The Train leak detection agent's systematic workflow seamlessly integrates with any existing pipeline management infrastructure, asset performance monitoring, and leak detection process. This has significantly improved my efficiency and scalability to handle many pipeline segments and instrument data together. Since this process is repeatable, I can perform it any time or across any segment and instrument data. It's a game changer, optimizing the leak detection process with minimal false positives, reducing operational disruption, and preventing unscheduled, costly maintenance. Thank you.